Okay, welcome everyone. Most of you know me, but for those of you who do not, my name is Caroline Still. I am the program manager from the National Security Innovation Network for the Challenges program. So here at Ensign, we connect non-traditional problem solvers like yourselves from academia and small businesses and ventures to the DoD community. And so for this challenge, we're opening up the aperture for AFRL by, soliciting proposals from academia, from industry, and small ventures. So we are so excited that you are able to join us today. We have with us the 4 semifinalist teams from the AI Planners AFRL Grand Challenge. So these teams have already met with the panel and we have heard their pitches and had a Q&A session. And so now this is an opportunity for the semifinalists to present your 5-minute elevator pitch to a wider audience and before we make the winner announcement live at the end. And so to kick us off today, we have Professor Frank Liebforth and Professor Oleg Ifiev from the University of North Carolina and Carnegie Mellon, respectively. So Frank and Oleg, if you want to take it away, I'll give you a 1-minute warning in the chat.
Okay, thank you. Yeah, great to be here and excited to learn about everybody's ideas. So I'm Frank Leipfarth. I'm an associate professor in chemistry. I'm an experimentalist. So my expertise is in polymer synthesis and developing automated reaction systems. And this is a close collaboration with my colleague Oleg Ifiev, who's an assistant professor in chemistry at Carnegie Mellon, and is really an expert in developing machine learning methods for chemistry applications. So when we started working with Oleg a number of years ago, and we have one paper published through our collaboration. And when we started working together, right, I was an experimentalist who really knew nothing about ML. So we started with a limited data set, as most experimentalists do, right, trying to, right, in a really large chemical space, understand the function of materials we were making. And of course, my group can build and deploy automated synthetic platforms. But thinking about problems in these really large structure spaces, we run into this curse of dimensionality. And we wanted a method where we could minimize experiments and maximize efficiency to quickly understand the function of our materials in this large chemical space. And it's one of these problems where we have, right, many interdependent variables that we're trying to tease out between. So it really motivated an ML approach because kind of our chemical intuition and the field's chemical intuition wasn't enough. There'd been dozens of papers working in this area and still nobody understood structure property relationships. So we came up with this iterative computational and experimental approach, which really leveraged active learning under both exploration and exploitation cycles. So in the exploration cycles, we would make a number of materials, right? We would feed that to Oleg's group, which would update their model. And then for exploration, right, that model would select the most informative experiments to do next to best build the model. And eventually we worked through about 7 cycles of this. And in the 8th cycle, we exploited the algorithm. This was when we had only explored less than 1% of the chemical space. And it turns out exploiting the algorithm worked really well. We found 4 to 5 materials that outperformed the state-of-the-art materials in the literature, even though hundreds had previously been synthesized. And the unique thing I found about this is numerous of those materials I wouldn't have predicted as a chemist would be the best performing. The other unique thing about this collaboration is we were spatially separated. So, my colleague Oleg, we were both at UNC when we started, but then he up and moved on me. And then a once-in-a-century pandemic hit. Right, so we were really doing the bulk of this work spatially separated, and the fact that, right, the computational work was kind of being done in the cloud, controlled at Carnegie Mellon, and the experimental work was being done at UNC really tested this, and I think made us work together even closer than we otherwise would have. So thinking about, right, some of the algorithms that Oleg will develop. Right, if you think about how we approach science, right, we all use a scientific method. One way to describe this that is typically done in the kind of biochemistry field is this design, make, test, and analyze. right? So we will certainly design materials, and my group will make them and test them. But in that design and analysis realm, what Oles's group is really going to pioneer is this automated machine learning approach. So, right, in a few words, automated ML allows, right, a data set to undergo testing through multiple ML hypotheses. So we're not bound to strictly using, right, neural networks or Bayesian optimization or Gaussian processes. AutoML will actually sample all of those and select the right hypothesis for the problem of interest. And we also have ideas here to layer on top of other more complex ML methods to kind of bring together multiple of these active learning cycles. And our project testbed in this case will be 3D printed elastomers. So that will be what my group will be making. Usually these have really, the properties of these are quite restricted, and that's because of, right, this this challenge that you need high molecular weight cross-linkers to not get nice materials, but viscosity limitations really limits you here. So all the current commercially available 3D printed elastomers are really in a small realm of strength versus strain. And we want to really use this approach to develop better materials. And so the deliverables of our project will be a general ML approach that is really robust and can be used by a wide range of people, that is really user-friendly. So, right, we can translate this to our colleagues in the DoD and they can adopt it. And that's validated by, right, us, especially at UNC, stress testing this and making sure we can create a method that even a chemist can do ML with. So thank you all very much.
Thank you so much. I did not realize I was on mute. Very much enjoyed your presentation. So next up is Dr. Noah Paulson, Professor Arun Manudi-Kanakitodi, and Professor David Fleming. If you would like to share your screen and begin your pitch. And I'll give you a 1-minute warning.
Great. All right, can you hear me?
Yes, we can.
And this should be full screen now.
It is.
It's really exciting to see everybody's work and to share our own ideas. I'm Noah Paulson. I'm an assistant computational scientist at Argonne National Laboratory. I'm joined by Professor Manudi-Kanakitodi at Purdue, Professor David Fleming at UC San Diego, and Marcus Schwarting at University of Chicago. We're talking about the Materials Oracle, a hybrid Bayesian and NLP framework for materials design. So the core issue here is obviously that the rate of materials discovery and development is really too slow to address many of the societal challenges that we face today. AI/ML can accelerate experimental and computational workflows, but it's really limited by the flexibility of those algorithms which are used to perform these sorts of discovery and optimization tasks. So what we're proposing is the use of natural language processing techniques through what we're calling a materials oracle to provide those sorts of critical insights and draw inspiration from other fields, as well as the entire corpus of scientific literature to sort of accelerate this discovery and provide innovative ideas to sort of initiate these sort of automated protocols. So we're proposing this workflow on halide perovskites for optoelectronics because both the space is extremely large and diverse, and also that there's a lot of potential here for societal impact, for example, high performance solar cells produced at lower costs. So we're proposing a 3-step workflow. On the right, we can see the first stage. We have the discovery of new chemistries using natural language processing, as well as density functional theory ML surrogate models, which have already been developed in the Manudi-Kanakitodi group. In the second stage, we're going to evaluate the synthesizability and also suggest probable synthesis graphs using these NLP techniques, and then also evaluating the suitability of those techniques using DFT ML techniques as well. And then finally taking those final candidates that pass these sorts of screening tests and pass them on to our multi-objective experimental synthesis optimization that is a facility that's already in place in the Fleming laboratory. So if I move on to the next slide, we can get into a little bit more detail about each of these stages. So stage 1, again, is the discovery of new chemistry. combining insights from DFT, ML, and natural language processing. On the left, we see an example of the Scholar BERT architecture, which is a sort of next generation transformer architecture that is being used on a huge scientific corpus from Wikipedia and scientific articles across many domains. And we're showing an example of this being used to identify different named entities within the text. So the idea is basically to automatically extract these named entities within limited numbers of articles in the text for the halide perovskite corpus, and then connect that to a schema that will identify structure, properties, as well as processing techniques to get there. On the right, we show an example of the architecture for this active learning surrogate model using DFT information as well as experimental information through a multi-fidelity workflow. And on the bottom, we can see the result of that effort in the development of this huge space of potential compositions used in the perovskite literature. And as we can see, there's a lot of opportunity here. The black X's show experiments that have been already performed, and these really cover quite a limited space of perovskites, but there's a huge opportunity to explore beyond that and obtain these sorts of next generation properties and performance. So once we get those candidates from the first stage, those new chemistries and new structures, we can pass them on and see, first of all, whether we consider them to be synthesizable. And that can be done using the natural language processing techniques, as well as using some of these DFT MD techniques, as shown on the parity plot in the bottom left with these sorts of formation energies for different compounds. And then we can also predict synthesis recipes using the materials oracle. And sort of the power of this is that we can generate synthesis recipes based on materials that have been already produced in the perovskite literature, but also materials that have been produced across the literature for other types of domains. So this is really adding a great deal of flexibility and also innovation to this suggestion of synthesis recipes. And on the right, you can see an example of the results that we might obtain from this sort of algorithm. This is a synthesis graph that's produced by the Fenning group that can directly be implemented in their autonomous experimentation setup. So then finally, in step 3, we take the top synthesis recipes and then we put them into this optimization loop, active learning loop with autonomous experimentation. We have a very large space of processing that we have to consider for these different steps. We can see mixing, spin casting. I'm sorry, I should pop that back just one. Annealing and measuring the properties. And we can see a video here of the autonomous laboratory in action, producing these materials as well as characterizing them. And on the bottom left, we can see the outputs that we can obtain from this, including things like the photoluminescence spectra, which is really critical for evaluating the promise of these materials in optoelectronic applications. So it's not only that we're going through this in one loop, we also have the potential to go through it again and again through stages 1 through 3 and really get the benefit of improving the natural language processing, including improving the ML and getting the benefits of those.
Thank you so much, Dr. Paulson. That concludes the 5 minutes. Thank you for your presentation.
Thank you.
Next up, we have Professor Teresa Windick from Iowa State University to present her STEAM solution. Teresa, if you'd like to take it away.
All right, thank you. It's actually been really fun to be involved in this pitch. We've not done this before, and I think we're learning a lot about all the different things going on, so we've really enjoyed this. So I just want to talk a little bit about our AI-based platform that we're proposing for chemical and materials design. The general idea is to have a modular framework that can build on our current capabilities and also enables the incorporation of new AI models and physical instrumentation as it becomes available to create an AI-enabled environment to aid experimentalists in their decision-making process. So if you're an experimentalist, you might have questions about, well, what reaction should I run next? How do I optimize the reactions that I have going on? And in our proposal, we suggest that there's at least 4 components that we need to be able to try to create a general environment to solve this for many different solutions. So one is to have reactions that and capabilities to connect to the hardware. The other one is an AI platform that allows you to look at many different kinds of AI algorithms. And all of that is coupled to a database with APIs that allows you to get at multiple different sources of data as well as having an interface that is user-friendly and available on desktops. So this builds on our platform that we've already built called Reaction Rover. And Reaction Rover is really made up of multiple different components. One of our philosophies is building a lot of components that can be reused and be flexible. And as part of that Reaction Rover, what we've built is something that will integrate well with different reactor components. You can swap in and out different reactor components. You can use multiple different online analysis capabilities and read all of that back into an automated or semi-automated or closed loop algorithm supervision that you can choose different optimization algorithms to then decide whether you're going to do the next step or what next step you're going to take. So the really nice thing about this is experimentalists can integrate any piece of this into their existing workflow already. So one of the key features that we think is important is being able to customize this for different laboratory setups, automating existing setups, or allowing the user to be able to integrate with different experimental apparatus. We've tried to make it so there's no programming required, so it uses the LabVIEW interface, and everything we develop is free and open source software. So currently we have those AI algorithms integrated into Reaction Rover, and we are in the process already of splitting that out to a generalized Python optimization API that allows us to use multiple different kinds of optimizers and AI algorithms, then to interface with the decision-making process so that you can benchmark against the different kinds of options. So as you all probably know, the field is very quickly evolving in the AI algorithm space. And there's only been some limited research into looking at which algorithms are the best for what particular kinds of science. And so this system that we're building is allowing us to get into that benchmarking activity. And it's all built on the database and APIs that will be able to take data from experiment as well as computation and be used in the AI algorithms to be able to make decisions and choices, which then can be fed back into the reactions. So, and we also hope to use existing data, right? We're not going to be creating all of our own databases. We're going to be using other people's work where possible. And then on top of this, we're building a layer that will allow you to integrate that material and to investigate each of these different components from a desktop environment, and to be able to integrate different data streams together, which is really important when a scientist is trying to come to their decision making. So the web interfaces and Jupyter notebooks that we are enabling here will actually allow you to look at multiple ways to use the data. And so our goal here is to actually integrate with the AFRL researchers, come up with some initial use cases, and really make this practical inside of the AFRL lab system.
Professor Windus, thank you. That concludes the 5 minutes. Next up, we have Professor Abigail Doyle and Dr. Jose Garrido Torres from the University of California, Los Angeles. Abby, if you would like to share your screen and begin.
Great, thank you. Can you see my screen?
I can, yeah. It's not in presenter mode. Now it is.
Okay, great, fantastic. Thank you very much for the opportunity. As Teresa mentioned, this is a new mechanism for me, and I'm really enjoying the process. So my name is Abby Doyle. I am a professor of chemistry at UCLA. In my research group is shown here. We are synthetic chemists, and in the field of synthetic chemistry, reaction optimization is pervasive and represents a complex, high-dimensional challenge wherein experimentalists must evaluate numerous reaction parameters such as catalysts, reagents, solvents, and temperatures in order to maximize or minimize one or more objectives. And due to the vastness of the chemical space, it is only possible to collect data on a very small subset of these combinations. This challenge is not unique to chemistry, right? And in the field of computer science, Bayesian optimization has shown excellent performance in algorithm optimization. BO is an active learning approach that uses the uncertainty and predictions of a surrogate model to iteratively select the next experiments to collect. So as a team of chemists from my lab, computer scientists at Princeton, and Jose, who is now a senior researcher at Microsoft, as well as some industrial process chemists, we have sought to develop and assess and apply Bayesian optimization methods for chemical reaction optimization. We have built what we call EDO Plus, or experimental design by Bayesian optimization. It's an open source code and web application that removes the programming barrier to use of the software for multi-objective optimization. We fine-tuned the algorithm components of EDBO Plus on experimental data sets that we generated in-house or obtained from the literature in order to sort of select the algorithm components that would be most effective for a chemistry application. And we've shown that its use on some new chemistries can enable experimentalists to make better informed data-driven decisions about which experiments to run in the laboratory through an online game where we had expert synthetic chemists optimize a reaction that the algorithm was also optimizing, and we statistically compared the decision-making between the two cases. So in the current call and for this work, we're proposing to develop and assess some critical sort of new functionality for EDBO Plus and integrate that into the platform. And then finally experimentally test that platform on some new sort of diverse chemistries, making use of some high throughput experimentation capabilities, robotic systems that we are building in-house at UCLA. So the workflow would start with a data-driven design of the search space. And so in this case, we'll make use of some sort of previously published graph convolutional neural networks that can select and suggest most likely sort of reaction conditions for a new reaction. And we'd use this to populate the conditions search space. Then we would follow this by initializing the optimizer using computationally inexpensive physics-informed features of the discrete molecules that are sort of within that conditions search space. A chemist then runs those experiments selected by the optimizer, and that the model is then updated and suggests a new set of experiments to run for the next round of optimization. And another feature sort of that we've included in the EDBO Plus framework is the ability to observe the predictions and uncertainty of the model at each iteration, such that a chemist can also sort of interpret the suggestions and sort of understand the process of the optimization and then contribute sort of from expert knowledge to the system. And so we're excited to sort of deploy this and evaluate it on both existing data that we have and on new reactions. And I appreciate your attention and for the ability to sort of participate in this call. Thank you.
Thank you so much. And thank you to all of the teams who presented their pitches today. I want to turn it over quickly to Dr. Luke Baldwin, who is the POC for this challenge on the AFRL side. Luke, did you want to say a few words before we make the winner announcement? You're on mute.
Is that okay?
Yes.
Okay. Yeah, thanks everybody for turning out. I just wanted to say thank you from the AFRL panelists. Really, honestly, the number and quality of the responses that we got have already made this a tremendous success, I think. We really do anticipate that, this sort of exposure is going to lead to other opportunities. And so we'd like to encourage those not selected to just continue to engage and just continue to lead in this community, because we think it will pay dividends in the future and that we're all kind of moving in the right direction. So thanks again, everybody, for such great ideas for this topic. That's all I have to say. Thank you.
Thank you so much. I know that I have certainly learned a lot today. And everyone's presentation has been so impressive. I wish we could name more than one winner, but unfortunately we cannot. So that being said, as was mentioned, while this was an incredibly difficult process and a difficult decision, there was one team today that stood out for their proposed reinforcement learning strategy that the panel felt best addressed the multi-mode and mixed system optimization aims of the call, while also spanning the synthesis and processing domains. And so that being said, that team and the winner of this AFRL Grand Challenge is the UNC and Carnegie Mellon team. Congratulations. It was very exciting to listen to all of your pitches. I do want to reiterate the difficulty of this decision. And thank you to everyone who took the time to put together proposals and presentations. It's truly been an honor to watch. I do encourage you to stay in touch. Please follow Ensign on social media. Please sign up for our newsletter. We have a lot of exciting opportunities that you could potentially participate in the future. So with that being said, thank you all so much for coming today. Please be on the lookout, all teams, for an email from me in the coming days and weeks with more follow-up information. So thank you so much. And with that, we can conclude this AFRL Grand Challenge. Congratulations again to the winners.